What if I told you there's a way to describe the entire universe? I'm talking everything from a simple pendulum swinging back and forth to a planet orbiting a star, not with a bunch of pushes and pulls, but with a single, super elegant idea. It's almost like a secret recipe for reality itself. And today, we're going to break it down.
I mean, we've all been there, right? You're staring at some crazy physics problem. You know, the one with all the ropes and pulleys and weights, and you're just trying to track every single force, every tension, every angle. It feels like you're fighting this tangled mess of arrows just to get one simple answer. But what if there's a better way?
Okay, so look at this. On the left, that's the classic way of doing things, the Newtonian way. I mean, just look at that pulley system. It's a headache, right? You got to account for the tension in every little piece of rope, the gravity on each mass. It's a lot. But then look to the right. That's the Lagrangian way. It captures the entire essence of that pendulum in just one clean line of math. And that's what we're talking about today, making that jump from the tangled web on the left to that beautiful, simple idea on the right. All right, here's our game plan. We're going to start by looking at why we even need to go beyond Newton. Then we'll meet the hero of our story, the Lagrangian, and the master equation that makes it all work. After that, we'll uncover its secret superpower, how it uses symmetry. And finally, we'll see how all of this gives us a totally new, much deeper view of physics.
Look, let's be clear. Isaac Newton's laws, especially good old F equals A, are absolutely incredible. I mean, they got us to the moon. But, and this is a big but, when you get to certain kinds of problems, like, say, a bead sliding on a weirdly curved wire, or that monster pulley system we just saw, things start to get, well, really messy really fast. And the real source of that mess, it's something physicists call constraint forces. These are basically the forces that are just holding the system together. Think about the wire pushing on the bead or the tension in the ropes. You don't actually care about those forces for your final answer. But with the old method, you have to calculate them anyway. It's like doing a ton of extra work just to have it all cancel out in the end. There has to be a better way, right? And there is. This is where our new approach completely changes the game. It just sidesteps that whole problem of forces by asking a totally different question. Instead of what's pushing and pulling, it asks, what's the story with the energy? And the main character in this new story? A little something called the Lagrangian.
So what is this Lagrangian thing? Well, we call it L, and the recipe is shockingly simple. Are you ready? It's just the kinetic energy of the system, that's the energy of motion, T, minus its potential energy, that's the stored energy, V. That's it, T minus V. This one simple formula packs in all the essential information about how a system is going to behave, and it completely ignores all those messy constraint forces.
Let's make this real with a simple pendulum. See that equation? Don't worry about the symbols too much. Just know that the first chunk there, that's its kinetic energy, T, and the second part is its potential energy, V. This one little line of math, that's the Lagrangian for the pendulum. It's like the complete DNA for its swing. Everything we could possibly need to know about its motion is baked right into that one expression.
Okay, so we've got our recipe, L. Awesome. But how do you cook with it, right? How do you take this little description of energy and turn it into an actual prediction of where something's going to go? Well, for that, you need a machine. And this is the engine that drives the whole thing, the Euler-Lagrange equation. Now, don't get scared by the name or the symbols. Just think of it like a magic black box or a crank machine. You take that Lagrangian recipe you just wrote, you feed it into this equation, you turn the crank, which is just a couple of standard calculus steps, and bam! Out the other side pops the exact equation of motion that tells you how your system is going to behave over time.
And this slide just shows you how powerful that machine is. I mean, look at all those calculations in the middle. But here's the magic. You don't have to be a genius and figure all that out from scratch. You just plug in your L at the top, you follow the procedure, and the correct answer, that final equation there in the red box, is guaranteed to pop out at the end. It's a totally automatic process. And notice what it didn't do? It didn't once ask about the forces holding that particle onto the curve. It just doesn't care. Now, this is where things go from being just a really clever calculation trick to something much, much deeper. The real power of the Lagrangian approach is how it uncovers this beautiful fundamental truth about our universe. It connects the simple idea of symmetry to the physical laws we see every single day. This is where this thing gets its superpower. And that superpower has a name, Noether's theorem. It's one of the most beautiful ideas in all of physics. And it basically says this. For every symmetry you can find in the Lagrangian recipe, there's a corresponding thing that is conserved, meaning it stays the same over time. So, check this out. If your system's recipe is the same today as it is tomorrow, if it's symmetrical in time, then energy is conserved. If the recipe is the same whether you do the experiment here or across the room, if it's symmetrical in space, then momentum is conserved. And if the recipe doesn't care what angle you look at it from, then angular momentum is conserved. It's incredible. And here's a perfect example. Looks like it's straight out of a physicist's notebook. See that note? It says L does not depend upon theta. Theta is the angle. So just by looking at the recipe and noticing that the angle variable isn't even in it, the physicist knows instantly, without doing any more math, that the angular momentum, that p theta, has to be constant. It's a profound shortcut to the deep truths of a system.
Okay, so what does all this really mean? Why does this energy-based approach work so well in the first place? It's because it's not just a new way to do math. It reflects a much more fundamental principle about how nature itself seems to work.
And this is the big mind-bending idea. Lagrangian mechanics completely reframes how we think about physics. It's a shift away from thinking about a chain of pushes and pulls to thinking about energy and optimization. It's like nature is always trying to find the most efficient path. When you throw a ball, it doesn't calculate forces moment to moment. Instead, out of all the zillions of possible paths it can take, it follows the one path that minimizes a special quantity called action. You can think of it like the path of least effort. And the Lagrangian method is just the mathematical tool we invented to find that one most efficient path.
All right, so let's wrap this all up. What are the big takeaways? First, Lagrangian mechanics is all about using a simple energy recipe, L equals T minus V. Second, it lets us totally bypass all those messy, annoying forces to solve really complicated problems. Third, and this is the beautiful part, the symmetries in the math point us directly to the deep physical laws, like the conservation of energy. And finally, this isn't just some historical curiosity. This is the language physicists use today, everywhere from quantum mechanics to relativity.
You know, the fact that so much of the universe's complexity can come from such a simple, elegant principle is just staggering. It really makes you wonder, doesn't it, if a huge idea like the conservation of energy is really just a shadow of a simple symmetry. The fact that physics works the same today as it did yesterday. What other deep, fundamental truths are still out there hiding behind other symmetries in the universe, just waiting for us to find the right way to look?